So in mathematics, a field is a collection of objects endowed with two operations. Addition and multiplication. Both of which are commutative and associative. And this field is going to be closed under these two operations. All right? So what does all this mean? Well, certainly we know what commutative and associative mean. So if I had A plus B, that's equal to B plus A. A plus the sum of B and C is equal to the sum of A and B and C. Okay? So I'm going to let A, B, and C be arbitrary elements of the field. And this is what we mean by addition is commutative and associative. Same thing with multiplication. All right, commutative and associative. Now the statement that the field is closed under these two operations can be thought of as akin to like the door is closed. You can't get out. So if you have any two objects, elements of the field, and you add them together, you'll get another element of the field. Addition can't take you out of the field. It's closed. Okay? Same with multiplication. Any two objects in the field, you multiply them together, you get another object in the field. All right, now there's lots of collections of objects in mathematics that satisfy this. Fields go a bit further. We also need an additive identity. Which we're going to call 0, that satisfies the property A plus 0 equals A for every element A of the field. All right? In addition to that, every element in the field is associated with another element, its additive inverse, such that the sum of that number and its additive inverse is the additive identity. Okay? All right, so that's fine. In addition to this, the field contains a multiplicative identity. Which we'll call 1, all right, such that multiplication by the multiplicative entity leaves the number invariant. Okay? Moreover, every element A of the field except the additive identity has a multiplicative inverse A inverse such that A inverse is equal to 1. Okay? So we got all these properties, one more, and that has to do with how addition and multiplication are related to one another. And of course, that's the distributive property. Okay, A times quantity B plus C is equal to AB plus AC. All right? For all A, B, and C in the field. Interestingly, it is this property that causes us to exempt the additive identity from having a multiplicative inverse. The reason for that is that A times B is equal to A times B plus 0 by definition. the additive identity by the distributive property, we would get that, and therefore AB is equal to AB plus A times 0. All right, and that would indicate that A times 0 is equal to 0. Let's prove that from these axioms. So AB is an element of the field, and that's because A and B are elements of the field, and the field is closed under multiplication. Now, unlike the multiplicative inverse, the additive inverse has no limitations. Every element of the field has an additive inverse. In particular, AB has an additive inverse. So I'll add the additive inverse of AB to both sides of the equation. All right? AB plus negative AB, since AB, or negative AB, is the additive inverse of AB, is 0. On the right-hand side, I'm going to use the commutative and then the associative properties of addition to combine these two together. And I'll get that. Of course, by the definition of the additive identity, 0 plus A times 0 is equal to A times 0. And that indicates that A times 0 is equal to 0. And this was true for an arbitrary element A of the field. The only reason I just went through that was to point out why we need these properties. All right? Part of the reason for the development of the concept of a field and then a ring and then, other things we'll be doing, vector spaces, all right, is to itemize exactly what is needed in order for us to be able to establish certain things. All right, and I don't need the same things to establish different properties. Some properties require more, some properties require less. All right? So at any rate, this is a field. A field, two operations, addition and multiplication, under which it is closed. Both are commutative and associative. Every element in the field has there's an additive identity, we'll call it 0. Every element in the field has an additive inverse, such that the element plus its additive inverse is equal to the additive identity. In addition, there's a multiplicative identity, 1, such that any element in the field times 1 is equal to itself. Okay? And then every element in the field except the additive identity has a multiplicative inverse, such that that element times its multiplicative inverse is equal to the multiplicative identity. Okay? And then we've got the distributive property. Anything that satisfies all of these properties is called a field. The most common fields, and the ones that we'll be interested in, are like the real numbers and the complex numbers. Okay? But the rational numbers are also a field. Okay? As are, in number theory, a lot of times people work with the remainders when they do modular arithmetic. So those can also constitute a field in certain situations. All right, but we're going to be interested in the real numbers and more generally the complex numbers as our fields. Elements of a field are often referred to as scalars. Okay, so we'll use that term a lot as we move forward.